So welcome back, everyone. So I hope you had a nice long weekend. Okay, so let's see. So I first wanted to review the schedule, and let's see, why is this guy over here? And so today in class we're going to finish chapter 1 in the book. We went through the material at the end of last week, Thursday. So too quickly, I'm going to review the calculations we did at the end. And in fact, that's most of the plan for the lecture today. We're going to review those calculations and kind of go through them with a bit more precision and look at a version of those calculations that involve the prior term as well. We had this prior term, which last Thursday we said, so we're just going to ignore this. But in the in the calculations today, we're going to see what happens when we factor in this prior and how to think about factoring this in. Okay, and then the other thing to notice is that quiz. So number 1 is is going to be on Thursday. You're going to have it's not going to open until if you go to it, you'll see that the quiz is there, but it's not going to open until 11:35 on Thursday. I will stop the lecture then. So at 11:35, so you can take the quiz in. So in the class, if you're taking it on Zoom, we'll try and monitor the questions on Zoom. So last time it was just me and TA Anna answering questions. So this time I'll make sure there are more TAs in the room, so we have more people to answer questions. Hopefully there aren't going to be as many questions on the quiz this time. So what is the first quiz going to cover? It's going to cover everything within chapter 1 that we also covered in class. So if you've had a probability class before, a lot of this will be review. If you've not had one before, this might be a little bit more, or if you're taking it at the same time, this might be slightly more challenging because you haven't seen all these concepts before that we went through so quickly. So I did a practice quiz this morning myself. I finished in 6 minutes. So it doesn't take that long to finish. It's not meant to be hard. It's meant to ask you about the main things that we covered. So if you understood the main things that we covered, you should be able to, to complete the quiz pretty quickly. I expect the average to be higher than 6 minutes, so I'm, I'm the instructor. I should be able to do it faster. But it's not meant to take the full 30 minutes. Yeah.
Is the quiz open?
Yeah, so the quiz is going to be open notes. And in fact, there's an option on the quiz so where you can get extra credit. It's going to be out of 100 points. The last question on the quiz is going to ask you to upload a sheet. If you do this successfully, you can get an extra 5 points on top of the score you get for the quiz. So you can get 105 for the quiz. So what is this sheet? I'm asking you. I'm going to ask you to make a cheat sheet for the quiz. I do this because I want you to. I think this is a good way to study. It should be it should be one piece of paper. If you want to make this on paper, and then so and then you can make it on a piece of paper with some handwritten notes, or and that's okay if you take a picture of it. So the format you'll be expected to be is going to be as a PDF, right? So have it. So you should have it on your device that you're planning to take the quiz with, so you can upload as part of the quiz as a PDF. So if it's optional, this isn't required. You don't have to do it, but you can get up to 5 points extra doing this, right? So it's suggested write down the core, most important things. So for that we covered in class, fit on one piece of paper. I think this is an effective way of reviewing the material for yourself, going over what you think is the most important parts. And basically, if you have that in front of you during the quiz, then it should be kind of very easy, because it should have all the most important things that we covered in class. Yeah.
So going over the quiz, like for practicing, do you recommend just going through the lectures and doing questions that we discussed in class, or questions from the book?
So if you look at the book, so the lectures follow pretty closely from the book. So I wrote the book from the lecture notes I prepared when I first created this course, right? So that's why they're so similar to each other. It's not, sometimes the examples change a little bit and some stuff is slightly different, but those are going to be pretty much the same thing. There are some extra things in the book, I think, where you might want a little extra information that I don't necessarily get to or cover in the course. Those things probably won't be on the quiz, right? So I think if you follow what I've been doing if you follow what I've been doing in class, that's the sort of the core stuff that's going to be on the quiz. The formal thing I recommend to do is to go back over the material and make one piece of paper that has just the front side of the piece of paper. So just one side of one sheet of paper that has the core information on it, maybe some examples to work through, or just, so some people just write down the core definitions, right? These are if you have this in front of you and you take the time to create a sheet like that, you should be able to do very well in the quiz. So in the final exam, I will allow you to bring in, I think, 6 sides of a piece of paper. So 3 front and back, or 6, one side of each. And those could be the 6 things you did during the quizzes, or you might have learned from your experience and figured out better what was the core material, and so you can update those things as well. But my official recommendation on how to study is to make this sheet. Yeah. So it is open book with other things. You cannot communicate with other people in the class, right? So you can't do that, but it is open everything that you can, so that you can find linked off the webpage. You can't go see if the answers are in Chegg, or if, so something like that. But so you can use anything that is linked directly off the webpage, or if you have the textbook in hand, you can use that. You can print out stuff as well. Okay, but there'll be one sheet. If you have the whole book printed out, it may not be as helpful as if you kind of collated everything into one sheet. You can make the font as small as you want. I've seen people have tons of information on there, but I don't think it's necessarily helpful as having, about the amount of information you can write by hand. So is that clear? Yes. Okay. Great. One other update. My office has changed. I'm now on MEB 3470. If you'd also like to find me on Zoom during that time, send me a note. I can turn on Zoom. This is still the 3rd floor of MEB. I'm still on the north side. That's what the 34 hallway is. The 4 is the north hallway. 70 is all the way on the east side instead of all the way on the west side. Okay, so I've moved office because of the roof construction project up there. hopefully only a couple of months. It's been a fun project. So okay, I will. There's one more thing I want to say before we get started. So in the first homework, there's a question that asks you to. So the fourth question asks you to do something like this code example I showed here. Just a general piece of advice so this class, we are not teaching you how to code. We're going to teach you some cool algorithms. The focus of it is not on the programming. The programming should be used as a tool to help you understand stuff. When you go out in the world and you're working as like a data scientist or something, most of the coding, when you do something new, there's sometimes you'll invent something new, you'll need to come up with it and write everything yourself. A lot of times what you'll do is you'll find something similar that someone else did and you will modify it towards your goals. That's how most of the Python kind of tasks you'll do in this class are designed as well. There'll be one thing about, I think homework 4, which will be slightly more complicated. Okay, but most of it, I'm going to give you examples of code in the class, and I'm going to ask you to do something that kind of modifies that code with you. And what I want you to learn out of the process is, okay, I need to change this function. What happens when I change it? And figure out what parameters to change to make it, look like I've asked you to do for for the assignment. That's what's happened here, right? So I've given you this piece of code and I asked you to change this to plot a similar thing for the Laplace function instead of the normal function as well. I suggest you start with this piece of code and you start modifying as little as you see necessary, but you can also play around with it, right? It's very easy to play around with stuff that's in one of these IPython notebooks or in Colab here. You just change it, you press it, it runs, you can see how it changes. Okay, so I hope you get a little bit curious and you try other things and you kind of, and you see what happens, but start here and make minimal changes and then, so that you can show me the output. All right, so that's what's expected here. They'll get slightly more complicated than this first example, but that's the method I expect to be learning in this class. You can look stuff up on Google to find out more information about other functionality within Python, because that's what you're going to be doing, once you're, out working in industry or in a lab somewhere anyways. Yep. How do you, let's see, if I click on it, I can say copy, right? And then I can paste it to something else. Yeah, you should be able to do like a right click or. Yeah, these are great questions to post on Canvas. I'm sure a number of other people do, and they probably know cooler ways to do it than I do, right? The normal thing is like a PNG. There's a ways to export this as PDF directly if you want to, but as long as the full documents, PDF will be fine to upload. Yeah.
As long as you can generate an image, not obliged to use Python.
You are not obliged to use Python. Everything is designed to use Python. The examples are, it'll be easier to do it in Python, but you're not required to. Yeah. The TAs will be able to help more with Python, but if you want to do it in other languages, you'll do other things that are going to be more complicated than this. But so this is a start. Plotting is in Python is an important skill to learn. So great. So, okay. So hopefully that gets you back on track with that, the quiz and the first homework. All right. I want to talk about, Bayesian inference today. We're going to take the maximum likelihood estimate stuff we talked about last Thursday and kind of extend this a little bit. All right. So let's restart with this. So I just want to go over this calculation a bit more. without rewriting all this up on the screen. This is from the lecture on Thursday last week. So we did this at the very end. I just wanted to go through this a bit more carefully first here, and then we're going to go through it again, okay, with slightly more correct notation or more general notation, and with the prior involved as well. But I just want to make sure that there are a number of tricks here which can be definitely confusing the first time you see them. For most of you, this is probably on Thursday was the first time you saw them. So let me just go through them again without writing stuff up, and then we'll get a slightly more complex example and go through everything again. So we had this, data set D, and we had these xi observations of this data set. And I said that these were independent, observations. Okay, and they were from some normal sort of distribution, which I wrote out the form of over here. I'll rewrite this more generally once I get to our slides, but just trust this is the form. And because they're independent, if I know that one, if I know that one of these, like this is the probability or the likelihood of seeing data point xi given this model M, right? And the model is parameterized by just the mean value, then I can write down the likelihood of seeing all of the data set as the product of these because they're independent. If you have independent, events, independent, random variables, then the joint likelihood of seeing all those things together is going to be the product of the individual terms, right? So the first trick big observation I've made is I can write down the joint likelihood of seeing a lot of my data as the product of seeing these individual terms, okay? And then remember, my goal was to find the model which maximized this likelihood function, right? The model which maximized the probability of seeing the data given this way of parameterize the model by M. Okay, right, and this expression was up here. Oh, okay. It doesn't do that again. And okay, and so I can just I want to find the maximum model. But the maximum is the same as the maximum of the log of the probability. A log function for something that's greater than 0 looks something like this, kind of plateaus. I mean, looks like it's plateauing, it's always increasing. The key thing is as the x value, which is the probability, think of this as the probability of the data given the model. As this increases, this value is the log of that, right? So this is the log of the probability. So as this one increases, this one also increases. Okay, so that means if I have a bunch of different models with different probabilities, the one that has the highest probability is also the one that has the highest log of the probability. Right, that one is up here. So I can maximize the log instead. And this log, it's adding a log onto something. Typically, when you have a calculus class, it makes it harder to calculate with. This is going to make things easier to calculate. We often do things because it makes the calculations, the algorithms actually easier. Okay, and so I can now maximize the log of the product of these likelihoods. And this is actually, and the log allows me to factor this and turn this into a sum, right? So now it's the sum, right, of the log of the individual, likelihoods. Okay, so this is a product, this is this equation about logs. Log of A times B is equal to log of A plus log of B. So I can decompose a product into a sum, okay? And then now I have this product or this sum I'm maximizing. And the nice thing is now the log is being applied to this expression here. And there are two kind of parts to this expression. Okay, it's a product of two things, right? The first term is the coefficient in front. That coefficient does not depend on m, and that gets moved over here. The other term has an exponential to start out with, right? And if I chose the log to actually be the natural log, right? So I replace this with the natural log here. Then the natural log of an exponent, those cancel out. And so the exponent goes away. And this first term here is now kind of a negative 1/8 times m minus xi quantity squared. And the second term does not depend on m, the choice of the model. So that one also doesn't matter in the max. For any model I choose that has the same value. Same with this 1/8 in front here. That 1/8, that's a constant factor in front. It doesn't matter what I chose here, so this does not matter. And so I want to, you can actually write this as arg min over the choice of the models of sum over xi in the data set times xi minus m squared. Okay, I've changed from an arg max to an arg min because there's a minus sign right here, and I've gotten rid of the minus sign in this conversion. Right, so this is, I've multiplied by, so -1. So I've multiplied by -1, the max goes to a min, right? So I've got a function, I've flipped it upside down. And now I'm minimizing the sum of the squared, so distances to my data set, and that turns out to be minimized by the average. If I take the average of these things. Yeah, great. Question. Yeah, so it's a great question. I want to cover other materials, so I'm not gonna do that calculation in class. You can write down this expression, you multiply it out, you take the first derivative and you set that equal to 0, and you solve for m, and it turns out you get the average. The calculations are in the book if you want to go see this, but that's it, yeah. Yeah.
So the way that we can use this is that we assume that the data points are independent, and we assume the model has a linear distribution, then we can find the average. Yeah.
So that's right. Yep. So we've derived, if you want to find a representation of data, one-dimensional data you think came with normal noise, the most likely estimate of the center of the distribution it came from is the average. So that's what we've done in this derivation, right? That's pretty neat. Okay. Okay, great. So there are a number of tricks here. Let's go and so revisit these, and we'll actually go through these again with a bit more kind of a bit more kind of advanced model. Oh, I'm still going through these parts of the syllabus. We haven't, so kind of I said we go through it in a bit more detail. So diversity and inclusion is kind of this is something I value. So personally in the classroom, if you are in this class, I want you to succeed. So independent of your background, so where you've come from, so the way you represent yourself, as long as that's inclusive of everyone else in the class. So these, there are a variety of categories. This depends on, we have, I think, a fairly diverse class, and everyone is welcome, and I will do my best to uphold this. So make sure everyone treats everyone fairly. So one particular aspect that we're asked to highlight in the syllabus is people's immigration status. So if you are so if someone is working, so if someone's in the classroom as a dreamer, or they have other challenges with immigration status, there's a variety of resources. There's the International Center, which affects a lot of graduate students I end up working with, and there's this Visit Dream website that that if you aren't aware of, and so this affects you personally, this might be a good resource to explore. So great. So okay. All right. So we want to talk about Bayesian inference, and so the first thing I want to do is to kind of look at a simplified version of Bayes' rule. And I'm going to introduce an important piece of new notation. Bayes' rule, okay? And we're going to have, we're going to write this as probability of a model. So given some data, right? This is the left-hand side. The right-hand side looks like the probability of the data. So given the model times the probability of the model. Okay. And so before in Bayes' rule, we divided the right-hand side by the probability of the data, but we're going to assume the data is known to us. And so we're going to care about, again, maximizing the left-hand side. So we're going to introduce a new notation. So looks kind of like an alpha or a fish. This is prop 2 in LaTeX. This means proportional to. Okay, so proportional to. Okay, and so it's not equal to, but if I have a function f of m, and I say it's proportional to g of m, that means this implies f of m equals some constant times g of m. Okay, where this is a possibly unknown constant. Okay, so it does not depend on the value of m, is what this C constant is, and I don't have to write this constant down anymore. Okay, so this is like the 1 over the probability of the data. Or if we assume that the model was also that the prior in the model was also a constant, we could also wrap that into the constant C as well. Okay, so I'm not going to write down this constant, and so this is useful that if I know and this should be positive. So C is greater than 0. Okay, so yeah, so it can't be negative, otherwise it flips the proportionality. Okay, but as the G function increases, then the F function also increases. Okay, so this proportional will be very useful, because before, and when I had to write down these calculations, I had to say the argmax of the left-hand side is equal to the argmax of the right-hand side, okay? And that, I want to take the argmax at the end, but in the meantime, I just want to know that the two equations were proportional to each other, so the argmax was the same, okay? This does not include an additive constant, right? An additive constant would also allow me to take an argmax or something. I will have to keep that around with this notation. Be nice if there was kind of another notation that allowed me to kind of handle that, but this is much more standard, just to say something is proportional to something else. Okay, so here I've written, this is a kind of a simplified version of, so Bayes' rule, that the probability of the model given the data or an event M given an event D is proportional to the probability of the data given the model times the probability of the model. Okay, I don't need to worry about the exact equation. This is the core part of Bayes' rule that so that I actually need. Okay, this is a good start, but this actually does not quite work yet for the calculations we did on Thursday, and so just reviewed, because I want to deal with when the model itself is not going to be discrete, right? Which we parameterize the model by a set of real values, and it didn't actually have a discrete value, so I can't actually talk about the probability, right? So I could talk about, yeah. So it becomes not quite mathematically right. So what we typically will do instead is to write these down as kind of these probability density functions. So I'm going to write it as a function, a lowercase p, m given d. Okay, and so this term will be called the posterior, and this is a PDF, right? So it's a probability density function, or it's a probably mass function. This is not necessarily going to be normal. Is not necessarily going to be normalized. Okay, and so this is replacing this term here. Okay, okay, and this will be proportional to. Now for this guy, I will write as so the likelihood, I'll write this as F of the data given the model. This will be called, this is coming here. This is the likelihood. Okay. Oh, there's stuff going on in the chat. Moved. Is there anything I'm missing in the chat? Okay. Okay, and okay, and so I previewed this again. This is also this one will be a PDF, the likelihood function. I should be able to control that. And then the last term here is the prior. And I will use this notation R of M here. This is the prior. Okay, and I'm just writing these down as functions that are kind of like probabilities, but these are, so PDFs. R is a term I use often. The prior, the most common symbol is actually a pi, right? The Greek symbol pi. And this is really confusing because if you write down the Gaussian, it has the constant pi in it, and then you have the product notation. And so I chose the value R here instead. Okay, as the prior. Yeah, question.
Why do the posterior why do they only apply?
Well, I could use these as discrete. For all, at least for all practical purposes, the definitions and notation for continuous kind of PDFs in place of probability functions and definitions work for discrete random variables so as well. Sometimes, I mean, there's some nuances that won't concern us in class, but this notation I think is more confusing. I'd rather write down probability, say the words probability when explaining to you. I think that's more natural for you to think of, more natural for me to say. And I can talk about the probability of the model instead of the prior of the model. you may not have a earlier notion of what did prior mean. And if I had started the semester talking about priors and likelihoods and posteriors, which is what the machine learning class probably does, then that's going to be confusing. So I'm trying to build up to this, right? Yeah. Okay. Okay. Good. Yeah.
You said the posterior was a probability mass function. What's the difference?
Yeah, it might not be normalized if I integrate the posterior, or if I integrate, yeah, if I integrate the right hand side. Well, yeah, if I integrate the right hand side, or depending on how I write this down, it might not integrate to 1. I'll probably density function, if I integrate it, it has to integrate to 1, but I won't need that property anymore. In fact, I often won't know what the integral of this is. And at the end of the lecture, we'll probably get to a few examples of things we can do with the posterior, where you don't need to know what the integral of it is. Basically, you can do things like compare two things, or you can sample from it. That's kind of beyond what we'll do in this class. But if you get to either the data mining class, it will cover this a little bit, and then there's a probabilistic machine learning class, which is awesome, which will come probably after a machine learning class, which talks about kind of using all of this cool machinery and stuff. Yeah. Right. So okay, right. So we'll talk about, I'll try and use these terms as well. The likelihood will show up a lot in the rest of the semester. And sometimes we'll have terms that will effectively act like a prior, or will explicitly be a prior. And then these will again show up later on. We'll try and keep most of what we do in this class the simple core ideas here. All right. Right. So, okay, let's go through a little example here. So let's go through, let's see, let's say I have a, I have a random variable h that I want to estimate. And I want to say that this is the height of average student at the U. Okay, so I want to estimate the average height of a student at the U. Okay, and I'm going to do this by drawing a bunch of samples, right? So D is going to be a set x1, x2 up to xn. Okay, and these I'm going to draw from say active UIDs, right? Let's say I can have a list of all the UIDs in the university, and I can draw a random sample, and I can somehow query someone's height. Okay. So I'm going to try and estimate the height. So from this data. Okay, but I'm going to start with a prior now. But I'm going to also have a prior. We'll call this R on right. We'll call this R on M, which will be the mean of a distribution, right? And I'm going to say that the prior is going to be a normal, a normal distribution, and I'm going to parameterize this by a mean. Mean of let me just write this as the whole model here. A mean of 66 inches and a standard deviation of 6 inches. Okay, so let's say my prior of what the height is going to be this of the model, right? And so this is going to be, let me write this out, pi over it's the standard deviation squared 1 over the square root times 2. So this is the normalization term I put in front, so that the normal distribution, if I integrate it, it always integrates to 1. Okay, and it's e to the power negative the mean minus 66 squared, okay, divided by 2 times 6. Yeah, actually, let me write this notation a little bit. Let me go back to this, where m is what I'm trying to estimate the mean of this distribution squared. Okay, so this is, hold on. Okay, well, I did 2 things at once. Okay, so this is the definition of the normal distribution with the standard deviation sigma, the mean mu, and the standard deviation sigma in the denominator inside the exponent, right? So I use exp because it's easier to see what's inside the exponent. And so now if I write this for the particular values that I've given, where the mean is 66, okay, so then, and the standard deviation is 6, I'm going to get 1 over pi times 72. That's 2 times 6 times 6 square root x minus m minus 66 squared 2 times, again, this is 72, right? Because that's 2 times 6 times, no, here, the 2 should be outside here. Yes, that should be 72. Okay, so this is my prior. My prior is now a continuous distribution. This is a normal definition. The normal question. Yeah. Okay. So this 72. My standard deviation, which was given to me, was 6. So sigma is equal to 6, and so this is 2 times sigma squared. And sigma is 6, so 6 squared is 36. 2 times 36 is 72. Right? We had 8 in an example on Thursday. That was from 2 times 2 squared. Okay. Okay, great. So this is my prior now. My prior is 66, a mean of 66. It's sometimes useful to think of plotting this 66 inches, right? And it looks like it's a bell curve, and the standard deviation, which is about halfway up, how far out it goes. Roughly, that's a standard deviation. It's got this is about 6 inches. So sigma equals to 6. This is mu equals 66 inches. Okay. So the first thing I want to think of is, let's say I took the average of D. Okay, and let's look the average of the set D, and I got 5.5. Okay, what's the first thing I should be thinking about here? I'm not going to do any actual calculations yet. We're going to go through and do some calculations. But what happens if I said, remember, the right thing to do if I didn't include the prior of taking a bunch of data, calculating the most likely estimator, was to take all the data points in D and to take their average. And let's say I took their average and I got a value of 5.5. And this is my prior distribution, 66 inches with with a standard deviation of 6. So this is about 60 to 72 inches is where most of the mass is. Maybe, if I go out a little further, 2 standard deviations, I get to 54 to 78. But I got an average of 5.5. What's going on? What should I think about here? Yeah. Yeah. So I mean, 5.5. Is 5.5 fit in this distribution? No. I mean, it could. It's not 0 kind of probability, or it is 0, but not 0 likelihood. It's not nothing, but it's minuscule, right? It doesn't fit this distribution. And so likely the explanation is the units are wrong on either the prior or the average, right? So what probably would happen here? Yeah.
5.5 feet would be about.
Yeah, so I probably got the units wrong, and this is 5.5 feet. Oh, if I took 5.5 and multiply it by 12, what do I get? I get 66. Okay, so one thing you can use the prior for is to check whether your data in the prior something is off. Okay, if it's off, and it could be units. Units are a common source of how things are off. There are lots of other things that could happen all the time, but just kind of check, make sure it's common sense is being aligned in the right. Yeah.
I was also going to say, you can also check the measure subpopulation.
If you're what?
Measuring a subpopulation.
Oh, if you're measuring a subpopulation, yeah. There are going to be lots of other kind of issues we'll discover, over the lecture. There are other things that could be happening here. You could be, if the average was 5.5, maybe I actually measured people at, 5.5 inches, very short, but this probably people, these infants laying down at the daycare, right? So that would be pretty short if that was the right thing. It could be a subpopulation, but in this case, yeah. So there are lots of other kind of data collection issues that can happen. So okay. All right. All right. So let's go through and do this a bit more detail now. So let's say that I actually have this data, and this is D, which is x1, x2, xn, and I checked, and this is now measured in inches. Maybe I took my old data, I multiplied everything by 12, so now I have everything in inches. How do we actually combine the prior and the likelihood together? All right, so let's review that the likelihood f is our function f of the data given the model, right? And so let's say that the so I'm going to write down this likelihood, and I'm going to say again that this is going to be a normal distribution. Actually, this likelihood will be the product of x in the data, where each g xi is going to be some PDF of where I think where I think this data came from. And I'm going to say now that g of xi is again going to be a normal distribution. The mean is going to be xi. Okay, so I'm going to say that the mean of this normal distribution, I'm going to say the mean of it is going to be m, and and this standard deviation, say, is going to be 2. I'm going to say when I ask for someone's height, remember I got someone's UID, right? And then I went and collected their height. Well, how did I go and collect their height? Maybe I went and tried to measure them, but probably I just asked the person what their height is. And there's going to be some error in this process because some people are going to lie. Some people are going to measure their height in shoes, or it's not going to be in shoes. I'm going to say there's a standard deviation of 2 inches I'm getting here. It's going to be unbiased with respect to the height. So it's going to be coming from a some distribution with standard deviation 2, and it's going to be a normal distribution with the true mean I want to estimate as the true expected value. Okay. And so now I can write this product down, write this likelihood as the product of xi and d of 1 over square root of 8 pi, right? This 8 came again from the standard deviation at 2, and multiplied by x of negative 1/8 times m minus xi squared. Okay, so this is now my likelihood, and this is actually should be the same as we had on that we talked about on Thursday last week. Okay, now I want to incorporate the prior as well, right? And so now I want to talk about the posterior. Okay, the posterior is kind of like, again, the probability of the model given the data, but now I'm not going to ignore this prior information I have. Okay, and I want to use the simplified Bayes rule to say that this is now going to be proportional to the likelihood, the data given the model, times the prior, which is the probability of this model here, right? And so, okay, and now I can write this as and now I can also say that the natural log of the posterior m given d is also going to be proportional to the natural log of the likelihood d given m given m here. Okay, so plus the natural log of the prior plus some extra term here, some constant. Okay, there was in proportional to, remember, there was a constant out front here, and it was a product. It was in this product. That becomes a sum, and its log, natural log of whatever this constant was, becomes that constant. I'm just going to write C here, okay? I'm just going to say some constant. I'm not going to pay much attention to it. I'm probably going to add stuff to it as going to become the constant will change. It'll be a different constant. It's not going to matter. It's still a constant. It won't affect my output. Okay. Okay. Now I can actually start to expand these things. This is proportional to the sum over xi and d. It's no good. Hopefully it's part of the thing I can control. Try replugging this in. Okay, that's
like the same thing.
Necessarily. It's just a placeholder for whatever model.
But it's a plus.
Well, let me fix one thing. All right. So great. So, okay. Okay, so now this is proportional to the sum over the data elements, -1/8 m minus xi squared plus -1/72 of m minus 66 squared plus a constant here. Okay. All right, this is the second term in the sum is directly from the prior, and this is the first term in the sum. Now this 1/8 and the 172 actually matter a little bit here. I can say finally that this is proportional to 9 times the sum xi in the data of m minus xi squared plus, or so minus m minus 66 squared plus some constant here. Okay, so I've changed the constant and I've multiplied everything through by 9, just so we can kind of see what's going on with the weighting here in the prior. Okay, so now it's kind of like I'm still there's a minus 9 in front here. Okay, so again, I want to maximize. See, the value of writing the proportional to is I didn't have to keep writing the arg max everywhere. And now I can say I want to take the arg max of this expression at the end. I can ignore the constant at the end, whatever that constant was, but I can't ignore completely the coefficients. What I've done is I've shown that the sum of all the distances to all of my data points is worth 9 times as much as the squared distance to the prior. Okay, this is what came out of our calculations. Okay. And that's because if you go through the calculations here, how come I got a 9 in front here? Why is this 9 in front? This is a coefficient of so this 9 is multiplied by the value of the data. It turned out it turns out that the standard deviation was a factor of 3 smaller, and so the variance I told you was going to be easier in calculations. The variance is a factor of 9 smaller. Okay, because I'm dealing with squared distances here. Okay. Okay, so the variance was 9 smaller on the data points I got from the students, and so that's why these terms, the sum of these terms was deemed to be each of them was deemed to be worth 9 times as much as the prior. Okay, and now I can solve for this. Right, so I know how to take an average, right? So what I can do is I can pretend I have 9 copies of each of the data points, and then I have 1 copy of the prior of 66. And I could solve for that. There's something called so that turns out I can solve this with, so a weighted average instead, right? Where I can weight these things by 9. What I can do is I could say that the weight of these things, I can say the total weight is going to be equal to the number of the data points. This is a set. I took the cardinality. That's the number of data points, n times 9 plus 1 prior, right? And now I can compute the weighted average of d and the prior as going to be the sum as the sum over xi of 9 times the value of xi plus 66, which is from the prior, divided by this total weight instead. So instead of just dividing by n, I had to weight these things by 9. And so this is a weighted average. It turns out the thing that minimizes, or if I get rid of the negative and then I minimize that, thing that minimizes that is the weighted average. Okay, it's just a simple extension of an average. So I can still solve for this. Okay, take all my data points, and I can calculate this here. So this is kind of the calculations. Okay, but what's actually going on here? Why did I get these numbers? This 9, it should be kind of mysterious. The fact that I kind of average in the weights of my data points and the weights of my priors, and somehow combine those together should hopefully intuitively make sense. The fact that it's completely a weighted average is because they're both normal distributions. Okay, if they were not both normal distributions, it would have been more complicated. I would have had to do, I wouldn't have been able to just take an average. If one had been if you use the Laplace distribution instead, that's you have to plot for your homework, it turns out that distribution does not have the square, and then the best estimator is the median instead of the mean. So if they're both Laplace, again, I can do some calculations directly. But otherwise, we'd have to use techniques we'll see later in the semester to try and find the right answer. Okay, but why is this 9 here? Where did this came from? Because the standard deviation was so smaller for the student data than my initial prior on the height of students. Okay, so what would happen if I said, well, actually, I said 66 inches, maybe I got that from like a national average. I got this from a study, right? So what if my prior R was actually a normal distribution, say with the mean of 66, but a standard deviation of 0.1, right? I said this is the average height of a student in a university. Maybe I found a study online where someone surveyed kind of 100,000 people across universities and found that, yeah, okay, my estimate of the mean 66 was correct, but because they surveyed so many people, they were able to get the standard deviation of the mean to be much lower, right? What we'll see the next 2 lectures after this one will be what happens when you get more and more data, what happens to your estimate. It turns out your estimate becomes more and more refined, and you get kind of your uncertainty goes down, right? We went from a normal distribution that, actually, let me draw it this way. So we're going to go from a normal distribution that looked like this to one that maybe has the same mean. It's not a great drawing here, okay, but they might have the same mean, but the standard deviation is much smaller. Okay, they both need to integrate to 1. That's why I had to slide this down a little bit. But the standard deviation becomes much smaller as I get more and more data. So let's say I actually drew this from a much larger distribution, my prior, and I have much more confidence in this prior. So the standard deviation goes down to 0.01. Now the ratio of the variances, the ratio of the variance so the var of D is going to be equal to 4, and the variance of the prior, the variance of the prior is now going to be 0.01. I've squared 0.1, right? So that means now the ratio is 400. Okay, so if I redid this calculation, it's going to be the arg min of the mean of the sum over xi in D, right, xi minus m squared plus the xi minus the prior value, and this is now divided by 400. Okay, so it means that the prior, if the standard deviation of the prior goes down, then this term has much more weight. It's approximately worth as much as 400 students. 400 data I collect, that's how much it would take in order to outweigh the effect of the prior, right? So as my prior becomes much more concentrated, I trust it much more. And it takes 400 students before I would trust that as much as the prior. Okay. So on the other hand, the other interesting thing to see is what happens with so more data. Okay, what happens as I get more and more data, right? And let's say the size of D of my data set, I'll typically say this is N. And as this goes to infinity, I collect more and more data. Let's say, it's I collect data from every student who's ever been at the University of Utah. Maybe that's 100,000 students. I don't know what the number is, right? As I get to 100,000 students, well, 100,000 divided by 400, this is still going to be 2. So is that right? So 2,500, right? So if I have 100,000 data points, this, even if it takes 400 of them to be worth as much as the prior, this is going to be, in sum, the effect of all these is going to be is going to be worth. Is it? Maybe it's 250. Yeah. Okay. Good. So 250, right? So it's going to be worth 250 times as much as the prior. So eventually, as you get more and more data, you tend to outweigh your prior knowledge, right? I guess, okay, maybe the University of Utah has students who are on average taller than the national average. I would start with the national average as my guess. And then as I got more and more data, I might start to trust that the data I have is more accurate than my prior knowledge. And so I'm gonna, as I get more and more data, eventually I'll say, oh yeah, I trust this data from the University of Utah more, right? And but I need more and more data to have it. At this point, if I only had 100 data samples, I might trust the national average more. Okay, yeah.
The sum term is only applying to this likelihood that prior on the side is outside of the.
Yeah, correct. The 400 is on here. Yeah, that's kind of a fact of, a coefficient to say proportionally how much is the data, are the data points worth compared to the prior information. Okay, and so these things can trade off in this way, and it's very clean to see when they both have normal distributions. Yeah. Oh, great, thank you. This was a mistake. Yeah, this was M also. Thanks, yeah. I copied that wrong. Did I get that correct here? Yeah, it's correct here. I copied it wrong. Yeah. Thank you. So right, okay. So there's other things that you could so possibly be concerned about this analysis. Yeah. Oh, so it's fine if it's either way around because I'm squaring them. Yeah, I'll probably swap those because it turns out it's not going to matter, right? with the Laplace distribution, you end up getting absolute value. Again, the order doesn't. Yeah. Right. So, okay. So there are lots of other things you can probably complain about. So this sort of analysis, right? So maybe the prior I don't trust as much because it's a different it's a different population. There was an issue. I said that the I modeled here as the standard deviation of the data from the so from the okay, so when I looked at this model, this is my likelihood model of a single data point. This, if you remember what this says, it says that this assumed that the data I sampled from came from the true distribution mean with a standard deviation of 2. But that's probably not what's going on here. One, it's probably bimodal. Men are typically so taller than women. So it's probably kind of a bimodal distribution. Probably the standard deviation is probably not 2 here. I use 2 just as an example. The standard deviation of heights is much more than 2 inches. This really isn't the measurement error so much as the modeling of the distribution of the noise. As I sample data from a normal distribution here, that this is a model of what the distribution of all the heights look like at the University of Utah, and 2 is probably too small here. Okay, but this worked out in our example, with the numbers we worked at here. Where did this so prior model come from? There are lots of different ways I could change this analysis, but these calculations were easy and I think illustrated the key points well. Okay, so when you come into this, one thing you'll notice when you're doing data analysis is I set something up. I told you, I said, okay, here's how the problem is kind of set up, and I did some calculations. And in this class, I'll try and keep the model so the calculations are easy, because I'm not trying to make it complicated at this level in this course. But there's a lot of choices I had to make here, and these were somewhat arbitrarily so choices of how I did this model. So it's if you question if exactly how I derived this, and if you're like in another computer science class and you have an algorithm, you say, okay, here's what you need to calculate. Someone gave you the specification. That's what you need to do, I guess, right? Maybe you can go back to them and negotiate. This is too hard or something. That probably doesn't work in class. But in your job, you could say, look, it'll take me 6 months to build like you want, or it'll take me 2 weeks to build this. That negotiation is part of the process. In modeling, it's definitely part of the process, okay? These models are flexible. We choose them partially so the calculations are easy, but sometimes you need to revisit those, okay? And that's, so that's important to keep in mind. So the last 5 minutes, I just want to very quickly say something about Bayesian analysis, and that what we talked about is the maximum a posterior estimate. Okay, this is the estimate that came from combining together a likelihood and a prior, and we just took the most likely estimate. But the posterior, the probability of the model, so given the data, this is much more powerful. We were saying the most likely model, but we actually effectively, the output, if we can write this down, is we are getting a function over the space of the model that says, okay, here's the distribution of where the model might be. This is what the posterior is actually telling us. Okay, we should think of it as we're parameterize it now just by one parameter. We'll look at multiple parameter models in the rest of the class. But we have this distribution over the models, And this means we can do a few other things about this. We can take two particular models, M1 and say M2, and we don't know the integral of this, and it's a continuous distribution. This will be more complicated. We get to higher dimensional things, but I can say the ratio of the posteriors, M1 given the data divided by M2 given the data. This is perfectly okay to do. I can look at the ratio. I can say that the posterior of M1 might be 3 times as much as the posterior of M2. We did something like this with the cracked windshield example. We said factory B was 6 times as likely to have produced my windshield as factory A, right? So this sort of comparison we can do. We can compare multiple models. This could be kind of a null hypothesis model and a new hypothesis model. Is this sufficiently kind of the ratio increased in a way that's so going to be large? We can also, as you'll see, if you get further along in here, there are ways, if you just can evaluate the posterior, you can sample from this distribution. I can sample a bunch of these models, right? So this might be M1, this is M2. I have a bunch of these models, and then I can do things like say, okay, what is the kind of not just the most likely, this value here, right? This is the map estimate, right? The map estimate is that model, but it could be the distribution is skewed. And if I looked at the average over these values, it could be that the average model weighted by their posterior might be different. This could be if there's a skewed distribution, these could be very different from each other. I can also say, let's say I want to actually compute some function. So I want to make a prediction, okay? And I want to make a prediction with the function that depends on this model. I can do something like I can integrate over the space of all the models of the function value times the posterior of the model, so given the data. Okay, so I can integrate over these models, and if I have a sample, it turns into a sum, a weighted average of the sample, which typically you can do. And this could be something where, for instance, let's say there's a magical threshold that everything over here is, the sports team, University of Utah wins the football game, where if it's not in that blue area, they lose, right? And so that's what I care about here. I will care about the fraction of times they lose, not what's the most likely outcome. The most likely outcome might be so that they lost, but they still won 40% of the time. Okay, so I can get these, or there could be some value associated with this. So if you're playing the lottery, the probability of the time you win a jackpot is very unlikely, but if you do win, it gives you a huge effect, right? There could be other continuous things like having to do with flooding, right? Of a 100-year storm, which seems to happen every 20 years, but a 100-year storm, it's a big devastation, but it's a very rare event, right? So I want to factor these things in, not just the most likely model of what will the storm, season be like this year. Okay, so the posterior, if you have this information, it allows you to do this kind of more advanced analysis. We won't be doing this in this class. I just want to give you a preview of what else you can do with this Bayesian way of kind of approaching the data. So, okay, we'll stop here. The quiz number 1 is on Thursday. We'll start in class at 10:35. Make sure to prepare your cheat sheet so you can upload that. Okay, you can get up to 5 bonus points for doing that. And then we'll start on concentration of measure in the lecture on Thursday.